All right, so yeah, I guess we'll get right down to business here. This is actually really great. We're still in the early stages here, so the fact that we have a smaller crowd means we'll be able to do more questions and do a little bit more hands-on later. My name's Brent Salina. I'm the founder of MICROrganic Technologies. We're focused on using microbial fuel cell technology for waste and wastewater treatment, and I found a way to apply that to the educational space. To start with, I always get a little bit of laughs when I tell people that I'm really passionate about wastewater. I usually have to justify why there's 55 gallons of it sitting in the back of my apartment. But there's a lot to be excited about, and we're going to be getting into that. So to start with, this is a picture that should look very familiar to you. This is the planet that you live on, in case you didn't know. But from this familiar image, there's a lot that you can look at it in a new way. One of the first things that you can take away is the fact that you can see it. There's light bouncing off of it and hitting your eyeball, which brings us to the next image, which is an overlay of a lot of green. That's the chlorophyll concentration around the planet. Now this represents basically the world's first solar cells. This represents photosynthetic activity and how plants are able to take CO2 and water and use it to capture the energy of the sun and fix it into the bonds in their constituent compounds. Now, the important takeaway in that is that anything that is living or was once living represents an enormous source of energy. It's all locked up there. You just have to have a way to get it out. And living things have figured out a really great way to do that. This small diagram here is a bridged representation of your typical cell. The way this all happens is going to be a little bit different in every organism. But this basically represents the toolbox that microorganisms have developed over billions of years to be able to draw the energy out of a wide variety of those compounds and use it to build up different compounds. Now, what's important here is that you look at all of the diversity that's here, and that's requisite because of all the different forms and compounds that energy comes from in the natural environment. In contrast, the way we do engineering right now is we generally tune our machinery for one or two of these. There's a reason that your engine knocks if you put the wrong gasoline in it, and it's because it's burning it as a different compound. Microorganisms don't have this problem because of this vast array here, but this is also the reason why things like biofuels tend to run into little hiccups, is that you have segments here that you're looking to skim off. Segments which the cell has very little interest in optimizing for your ability to crack it open at the end of its life. Now, in contrast to that, this right here is the cell's respiratory cycle. This is where, when the cell picks up a material, all of the energy winds up going to. This is where it breaks it all down. This is where the final electron accepting happens. And we'll get more into what I mean by that in a little bit. But the really important takeaway from this is the fact that every pathway on this map more or less either feeds into or draws from that. So that's the focal point, and if you could, that's really where you'd want to tap into the process. We're going to...
Back in the cell, is it like the mitochondria?
Yes, yeah. We'll get a little more into that in a bit. Now, to diverge for just a second here, this is the way a traditional fuel cell works. In short, we rely on chemistry happening through a wire. All chemistry is electrons jumping from one chemical species to another. In a fuel cell, we force it, and in any electrochemical cell, we force it to happen through a wire so that we can take advantage of that moving current. And it works something like this. You have the hydrogen gas that deposits its electrons onto the electrode, developing hydrogen ions, and obviously the electron that then travels through the wire into the cathode compartment, where it's joined by molecular oxygen after the hydrogen ion migrates over, wherein they all combine to form water. Now again, all we did, those species under the right conditions would interact directly, but by having that membrane there, we force them to do that interaction through a wire so that we can take advantage of that current flow by putting anything in between. You could get into the details of all the electrical engineering behind that, but it gets fairly complex. So again, that's the real takeaway, is that all chemistry is electrons jumping around, and electrochemistry is forcing it to go through a wire. How that relates to biology is that biology is still chemistry, and therefore you can do a similar process. And what that means is that we can take advantage of a lot of those processes, such as glycolysis, respiration, and various anabolic and catabolic activities. The one, again, we're going to be focusing on based on that other diagram is respiration. So in answer to your question, this is how it happens typically in a cell, right? This would be in the mitochondria, and the electrons that are getting shuffled around as all of your food changes into different forms and gets broken down winds up getting deposited on oxygen here. So that's the way that it would go in a typical eukaryotic cell. Now that's really important. That's a very important concept, because the reason that that developed to begin with is that by using oxygen, organisms are able to get the most energy out of their food. It's similar to how a car engine doesn't run well if it's not properly carbureted. So that's really important, and that means that where those electrons go after being shuffled around determines how much energy the cell can get for the food that it had to work hard and take advantage of. Now, this is a fairly crude diagram, but we'll pretend for a second that this is a slow-moving stream. Oxygen isn't particularly soluble in water. So in the absence of large waterfalls and eddy currents and things like that that are going to churn the water and introduce a lot of oxygen, there's really not going to be a lot of it at a certain depth. So up top, you have lots of organisms that are able to get this oxygen and deposit their electrons on it, and then turn that into water, like we mentioned before. In contrast, this guy down here is not going to have that ability. He doesn't have a terminal electron acceptor. So what microorganisms have developed the ability to do is, rather than use that oxygen, they'll use minerals and metals that are in clay sediments, deposit it there, and now they too are able to get that kind of fuel efficiency. This leads to them being able to fill an open evolutionary niche, and they therefore proliferate and are seen abundantly in nature. Yay. So let's go back to our fuel cell now, because this is where it really starts getting exciting. Now we can take that design that we had before, and we're able to throw a biofilm of those microorganisms that we talked about before on the anode. So now what they're able to do is take organic material as opposed to hydrogen, although they are capable of utilizing hydrogen, and they process that into hydrogen ions, just as before, and electrons, just as before, which again, just as before, travel through the wire, and the hydrogen ions migrate through, where they're all joined by oxygen, and they form water. So that's where the name comes from, is microbial fuel cell. And this is the way those first reactors worked. Now again, because oxygen isn't particularly soluble in water, we had to put an air stone in here to be able to, like we were talking about before, keep bubbling in that air so that there was enough oxygen for the cathodic reaction to take place. But what's unique in comparison to a regular fuel cell is we can nix that membrane. Remember before, the reason that we had it there was that so those species didn't interact directly. We wanted to force them to do that through the wire. But cells have their own membrane, so we don't really have to worry about that as much. And in addition, like I said before, because oxygen isn't particularly soluble, there's not really enough of it to migrate over to the anode where the bugs are in most cases. In addition to that, the really exciting part is that we can do something really special with our cathode now. We can coat it in Teflon or another hydrophobic coating that keeps the air on one side and the water on the other, but still allows the oxygen to come through. If we do that on a conductive material like carbon felt, that means that we are able to take molecular oxygen to combine with those electrons there. Now that's really important, because while oxygen isn't particularly soluble in water, there's apparently enough of it in the air for you and I to do okay. It's present in about 20% as opposed to less than 1% in water. And that leads to a reactor design similar to this. Now that's a single chamber reactor, which, again, you can put anything that will decompose inside of that, and the microorganisms will use that plus the ambient air to make energy, which is really cool. This is an electron micrograph of what the bugs actually look like. So I always really like this picture because you talk about bugs plugging into an electrode there, and they literally do that. They form these conductive pili-like appendages called nanowires that literally plug directly into the electrode. The best analogy I can think of is always the scene in The Matrix where he pops out of the pods there. I always like to imagine what one of the bugs might do if it suddenly gained consciousness and was able to see what's going on. But That hasn't happened yet, so we don't have to worry about PETA getting on our case about that.
So can I ask you those
Sure.
things there, the wiry looking things?
Mm-hmm.
Is that bacteria, the microbial?
Correct. Yeah. So they're
Grow them?
they're predominantly from the genus Geobacter, and what you can do is actually enrich them from pretty much any mostly anoxic environment. So mostly anywhere where oxygen is going to be limited. Now they start in a fairly small quantity, but and that's because that you generally don't have that cathodic reaction happening a lot in nature. The rates are tied. You can only deposit an electron as much as you're getting it accepted on the other end. So in these cells where you have a nice cathode going, the bugs will do really well. In nature, they do well enough for you to find them pretty much anywhere, but they're not the predominant species. So what I'm saying is that if you take a sample and you put it in one of our reactors, because they're more fuel efficient, they will start to do better and better and better than the other species that are present, and eventually you'll be able to enrich them. But,
So the original sample of bacteria, there's not that many of them.
Correct.
And then as they grow, because they do great in this environment, the other bacteria die off.
Correct. So you actually get an example of selective evolutionary pressure that you can monitor by using something as simple as a $6 multimeter to watch the voltage rise over time.
How long does that take?
That can take, well, it depends on how good you want it to get them. Some labs have been doing that literally for years. You can get demonstrable results within a matter of weeks. And a lot of that, too, also depends, like I said, on where you get your sample.
Sample of bacteria.
Correct.
So, but you originally said that the bacteria, you have, in your thingy, you have the bacteria already coded onto your...
Yes, we've been enriching that for a while. So they literally grow, you put the liquid in, and the bugs will find the electrode and attach them.
But they don't want to attach to the cathode, only to the anode.
Correct. Yeah, because the cathode's where the oxygen is. You'll get, it's actually another problem. It's not an issue in these cells in particular, but that's actually another problem is in those single chamber air breathing ones. The electron depositing guys don't want to be there, but there's plenty of other things that'll use that as a substrate, and that can gum up the whole works. There's a whole lot of intricacy there, which is actually a great thing, and Brian will be touching more about how that impacts kind of the whole educational aspect. Yeah.
On the bottom kind of right side where it looks like they're all kind of connecting to, not the actual bugs, but whatever that solid mass is right there. What is that?
That
is
would,
the cathode or
that's the anode electrode. That would be a strand of, I believe this is carbon felt. So that's literally just like one of the little, I should mention that. We use predominantly carbon-based materials for the electrodes because they're conductive. They're cheap, which is great, and they also, by being carbon-based, the microorganisms have a really easy time attaching to them. So it's kind of, we get all of those advantages. Yeah, and that's literally, that would be the electrode right there. One of the things I should say is this is actually a fairly cleaned up image. In the process of preparing this, you take it through a couple of cycles that get away a lot of the gunk. Kind of naturally, you'd see a lot more junk in between that serves to increase conductivity. And in general, biofilms have a whole lot of activity going on that allows the cells to communicate and generally assists the process. But this was prepared to look at the nanowires specifically, so they kind of just washed all of that away. And that's great. So we just did something absolutely amazing. We took microorganisms, and we were able to take a toolbox that's been literally billions of years in evolution and can break down pretty much anything that you can think of that would decompose and turn it directly into electricity. Unlike anaerobic digestion, we don't have to purify the gas coming off of it. All we have to do is a little bit of power conditioning. And that's a big, big story. But as it turns out, the power output on these is not all that high. There's a lot of potential for the technology, but we're actually going to be starting somewhere a little bit unexpected, and that's why I've got all the sewage in my apartment. So we start with wastewater, and the reason is that wastewater is a very large problem in the United States and everywhere. We produce 30 billion gallons of it, and it costs us an enormous amount of energy to deal with. Depending on whose estimates you're looking at, it's anywhere between 3 and 5% of the nation's total energy expenditure. So let that sink in for a second. That's 3 to 5% of every watt hour that's used in the United States. And again, the real irony in this is that organic material is incredibly energy rich. It's just a matter of pulling it out. So our solution is to be using this as a treatment process that uses its own burdensome material that it's looking to dispose of as the fuel for its process. And one of the things I do like to cover is, because some people are fairly, not sure of why we even do wastewater treatment yet. A lot of people will say, well, it's a natural process. Clearly we've been doing this and animals do this for, billions of years. What's the problem? Won't nature just take care of it? And the answer is yes, but it doesn't mean that we'll particularly like how it does it. And the main reasons for this are, again, where those electrons are going as the microorganisms deal with this food source. And we'll start with talking about the effects of when that's oxygen. In short, when you have a lot of food, you're going to, even in a really nice turbulent stream, you're going to get a lot of microorganisms. A lot of microorganisms with a lot of food means that they're using up a lot of oxygen. And that stream has a limit to how much it can reintroduce due to the upstream processes with all that churning. So if you overwhelm that limit and all the microorganisms use it up, you wind up with things like fish kills that you see often in algal blooms and other like processes. In addition, when those microorganisms use carbon instead as their final electron acceptor, you wind up forming methane. Now, methane's great in processes where you're trying to generate biogas, but it's really hard and financially not feasible to be harvesting it off of something as big as a lake or a stream. You're just not going to be able to do it. And that's really bad because methane in and of itself is about 20 times worse of a greenhouse gas than CO2. And the last one is when those electrons wind up getting deposited onto sulfur-containing compounds or sulfur itself. When this happens, this particularly expedites river acidification, which again just completely shifts the natural ecosystem. And you can wind up with different fish species being run out of the river, as well as it's polluting our natural aquifers. And that brings us to the most important point, and it's that water isn't used, it's reused. We have the same water on the planet now that we had as when everything started, more or less. So that means that we need to take care of it so that we actually have something to drink. Fairly important in biology. And this is why we do wastewater treatment, and it looks something like this. You have homes and areas that use this water, and then in general, it winds up going to the treatment plant where it's processed a little bit to remove some of those organic materials, and then given to the natural aquifers for further purification. The systems that already exist. So that's the big point, is that, again, nature does do an okay job of taking care of this, but it has a limit. So essentially what we do is we pre-digest the organic material before it's introduced to those aquifers so that they're operating at a steady state and we don't overwhelm them and we can continue to get water that we can actually drink. And that's important because as it works out, if we don't do that process, we have a harder time getting drinkable water. So we can either pay it upfront or pay an increased cost for water that we can actually consume safely on the tail end. So that's why we do that. That's why it's paramount to our growth. And actually, wastewater treatment has been tied to population and quality of life increases every time that it's been implemented. But the biggest energy hog of this process by far and away is a process known as aeration. Again, when we were talking about what's going on in the river, you have the water flowing by over rocks and just down various cascades, and that gets the water churning and introduces that oxygen. We can replicate that in the plant. What you see here is a paddle wheel at the Rensselaer County Wastewater Treatment Facility, which basically is a giant poop blender. Throws it all up into the air, gets all that air introduced, and makes it so that those microorganisms now, they're using oxygen, not generating those acidification compounds and not generating that methane, but they're also doing it in an environment where we don't have to worry about any fish dying if the plant's operating properly. So again, take that back to our fuel cell. We can do the same thing. We can introduce oxygen, but now we don't have to spend all of that energy to churn all this around. So we actually generate a little bit of electricity while we're doing the same aeration. And that brings us to a really interesting market opportunity, and why I got involved in this is the fact that compared to other alternative energy technologies, while we're working on bettering the power output, we can actually address a huge problem. I mean, how many times have you heard solar say that they'll be able to be profitable before they generate a single watt hour? Doesn't happen. Wastewater treatment is such a big problem to begin with that we can be profitable as we do that and increase the technology and roll it out in subsequent generations. So that's really exciting. That doesn't have a whole lot to do with education, but I get happy about it. And that brings us to our company's motto, which is 30 terawatts in 30 years. There's enough energy in sewage alone to meet about half the nation's energy demands, or that which is currently met by coal. 30 terawatts in 30 years comes from the idea that we'll be able to increase the power output and start drawing more and more organic sources, from yard clippings to anything, again, that will decompose. That is enough to replace the demand currently met globally by coal, natural gas, and oil combined. Oh, absolutely.
So in one plant, how much watts are being generated from that right now, this process?
Oh, right now they generate 0. I mean, we're scaling this up. This is new technology.
Oh, so there is no size plant?
No, absolutely not. We're building it. Yeah.
No, there's the poop kettle.
Oh, yeah, sorry. Yeah.
You have to put everything in, right?
Oh, yeah. Oh, yeah, no, that's how they do it now. They, how many it consumes? Yes, okay, yeah, that'll, it depends on the size of the plant, but Albany County has 2 plants that are about 20 million gallons a day, and just to put it in dollars and cents, that'll be about $400,000 in electricity a year.
So this technology would be introduced to those water treatment plants, pre-digesting before that water is then treated, and that electricity, how much
Well,
are you
anticipating
generating from that process?
Well, to start with, to be perfectly honest, we're not even looking at generating it. We're looking at just nixing that power consumption. The reason being is that until you can produce enough electricity, you do have to do a little bit of power conditioning, which gets complicated on a larger scale. And being a small company, if we can get something on the market where we're just able to cut that bill, we're going to go with that, and then do the rest of it when we're not starving. But in terms of how much energy you'd be able to produce, there's a really elegant aspect to the fact that your fuel source is intrinsically tied to the local population. So as the local population grows, so does your fuel source, and so do your treatment needs. So it's really nice in that fashion that you'll have the energy you need locally, just inherently. So now we're going to start segueing into a little bit of how this can apply to you as educators. And one of the big things that we've actually found an unexpected amount of traction with is the story of how all this started. I literally started this company in the back of my apartment. It's been a very, very interesting process. Every startup has this chicken and egg cycle where you need the money to get the data, and the people that want to give you the money want to see the data, and that just keeps going and going. And once you start working through that cycle, it picks up steam a lot like a freight train, but that initial push is absolutely enormous. And we've had a lot of interesting experiences overcoming that initial bump. What you see on the left there is a kiln that we used. Like I said before, we can use Teflon as part of the coating. Now, Teflon's pretty readily available. It's all over your pans. And if you want, you can actually buy a spray that you can put on there and re-coat it by putting it on the skillet and heating it up. Now you can imagine for a kit about that big, doing that on a square wouldn't be terribly difficult. But when we're trying to do scale up and I have to do electrodes, this big, I'm going to need a fairly large oven, and those can be expensive. So we bought a $50 kiln off Craigslist. I electrocuted myself a couple of times trying to rewire it, burned myself a couple of times, but we got the job done. That center thing, when we make our catalyst for the cathode there, it's nitrogen-doped carbon powder. We boil it in nitric acid, which I was able to get off a shady corner of the internet. And that's us doing one of the refluxes out on my back porch this summer. I was kind of joked that if, for whatever reason, the police ever decided to walk through my apartment, they'd probably be taking me with them on the way out, and I'd have to explain to them that I'm playing with sewage, not manufacturing illicit drugs. And this is, my apartment here during a particularly busy week this summer. I have a very uniquely understanding roommate. But the point here, and how this all relates to what we're doing here, is that one of the reasons we started working on this technology is it's clearly accessible. You know, these are not clean room conditions, and you know, this is science that we've been able to get to the point that now we're talking about industrial partnerships. You know, we were literally able to build this in our apartment, and when we talk to kids, that's really great because that can help to drive the message home that, you know, no, this isn't just for the sake of a learning process. This is real science. And with that, I think that would mean, oh, right. You know, we're going to wax philosophical here for a minute, but this is one of, you know, my favorite stories. You know, as I was doing this process and all my friends were, you know, graduating and I was looking at being gainfully unemployed, you know, as we were all leaving school, you know, I really had to justify why it was I was sticking around, and you know, they shouldn't be calling someone that had a straitjacket in the car. And this is one of those stories that really, you know, helped me out with that. You know, we're all taught when we talk about the Wright brothers, you know, when you're in school that, you know, nobody thought manned flight was possible and they did it, and, you know, et cetera. And that's a great story, but as it turns out, the truth, as usual, is actually a lot more interesting. People knew manned flight was going to happen. You know, there were people following it. You know, they knew that people were working on it. They knew it was going to happen. In fact, the Smithsonian was so sure of it that they sponsored a man to make sure that it happened. You know, he was a great, he knew his physics, his engineering came, you know, had all the credentials. If anybody was going to do it, it was going to be him. And I don't know if anybody knows his name. Probably not, because he wasn't the Wright brothers. They were two nuts that had a bike shop and were trying to throw planes together out of bike parts. And you know, lo and behold, they had a little bit of success. And 66 years later, we're leaving footprints on the moon. So, you know, that kind of keeps me going, and that's a really great message to send along to kids that are just looking to start what we hope will be STEM careers.
Can you hear me? Okay. I'm Brian. I do kind of the educational side of microorganic tech, which again developed out of Brent's apartment, out of the back room doing industrial fuel cells. And we, or more him, I kind of came on later, we realized that there's a huge educational market for this. Just the principles that are applied, everything that we do can easily be translated to education, both elementary to secondary, even middle school, anybody. Next slide. Yes. Yeah, they can make great lesson plans. Next slide. So we started out by working with schools. We've had a number of contacts in the Skodak School District, Skodak Central. One of them was Ken Malloy, who's a tech teacher, and he wanted to do something with microbial fuel cells or alternative energy. So we came in, did some lectures, did some tutoring, some mentoring, and eventually it grew out into a whole year-long project where they would work on it for a little while over the at the beginning of class, and then they would move on to other things. And by the end of it, they developed this fuel cell themselves. The kids designed it. There's a full notebook here with all of their engineering decisions, justifications. It's very interesting, and I encourage you to look at it because it's amazing work, especially from juniors and seniors in high school. It's like, oh, there was a sophomore in there too. Yeah. And we really want to grow this initiative. Education has been a huge part of our lives. It's given us incredible opportunities. I wouldn't be standing here today without it, clearly. And the opportunities for advancement are huge in STEM. There are jobs opening up everywhere. Vermont just opened up or started a program where if you move to Vermont after you graduate from school and get a job in STEM, work there for 5 years, they'll refund the senior year student loans that you have, which is pretty cool. Great way for job growth too, but it's all STEM. That's where the jobs are. But MFCs are an interdisciplinary STEM platform that real-world problems and applications, as Brent said, it treats wastewater, generates electricity, it can do great things for the world. But the concepts that are involved are very easy to understand. They can be boiled down into things that elementary school kids can get the gist of. But the research is so modern and cutting edge. Those bottle reactors that Brent showed you are from 2004. That's about the earliest that this research has really taken kind of a concrete footing. So we're right on the cutting edge of everything. Like I said, it's the ideal STEM learning platform. It covers areas of STEM, all areas of STEM, but starting with science, it does biology, physics, all these are all biological principles that it can cover. And it's an expansive list. Like, it could be overwhelming for secondary school kids, but you can boil it down. I can give you the whole list if you want to read it, but they all make organic connections with simpler concepts, and you can use them to teach kids about small biological processes and be able to see, well, this is how it works. This is what you can do with it, which I think is really cool. And in any depth, in any depth, these can be used as a subject for a PhD thesis. It's just what level the kids get into, which is really cool. And because of all these processes, the kits can be used in biology classes, in chemistry classes, in physics classes, which is amazing for a single device. I guess I already explained this. Yeah, there, technology. You can use it as a DC power source for circuit design, which is important for Project Lead the Way classes. I know that there's a class in digital electronics where they do circuit design and basic stuff like that. And you can use it as a power source for testing or whatever. But you can also just teach it as a kind of an engineering stepping stone. You can use it to teach CAD modeling because there are components into it. There's engineering components, which I'll get to right now. Many, many, many concepts related to engineering. Material selection. Kids can experiment with it, try to improve efficiency by increasing the surface area of the electrodes, the spacing between them, try different membranes, work on mechanical sealing. It's really amazing what you can do with these things. And everything's intuitive, making it a great test bed for them to just kind of try new things and see what they can learn. Now, math, it's used in all science. It's very important. You can use it as a way of collecting data for statistics, do statistical analysis of things, plot trend lines, all that. But the real important thing is informal education outside of class. That's where the real learning happens. And it goes without saying that kids learn best when they're interested, having fun, and self-motivated. And this quote kind of boils down to everything that we want to do with microorganic tech, education anyways. It is a miracle that curiosity survives formal education. Kids are so often taught to the test, and this is what it is, like, everything seems like work to them. That's how I thought about a lot of things in school. Like, oh, I have to do this, I have to do this, I have to do this. Where's the fun? And I had a great science teacher who brought in all these guest speakers who just did really interesting things. And it just kind of opened my mind up to see, yeah, science is fun. This is what people want to do. It's not just work. And so developing curiosity is very important. I played with Legos as a kid. And that's one of the ways that I really kind of got involved with engineering at first, and then product and graphic design, which is where I ended up. Just kind of putting things together, taking it apart, seeing what I can do. It's a great way to learn, just playing around, basically. And this is kind of an informal stepping stone of how we've noticed that kids learn. They can, when they wonder something, it's important that they go look out and ask questions about it, try to figure out what it is. But if they can't get immediate answers to those, that shouldn't discourage them. They should try to figure out the answers to those questions themselves, and that's how they learn. And going into schools and building the fuel cells and speaking to students and all that sort of thing, we have we have observed that students have done really well with this stuff. They've, sorry, I'm kind of losing my train of thought. We've, where am I? They've done really well. They've learned a lot. They've become curious. They've really wanted to do more with it, and they've asked a lot of questions, which we think to be a huge success. We've also noticed that kids are motivated by our story, like Brent said. We started in our, or he started in his apartment, and we just grew from there. And it makes science relatable. Kids can think, oh, this is science that people actually do. It's not clean room science with million-dollar equipment. This is parts we bought at Home Depot. This is research that we did just on the internet half the time, trying to figure out exactly what biological processes we could use, how to apply them, what we really need to do to make this work. And then using that, we can use our full college educations to really expand on that. So what exactly do we do at microorganic education? Well, one of the things we do is the fuel cell kits, which we do sell. They're basically small models of the two-chambered kits that we develop for industrial applications, or we're developing for industrial applications. These are ones in use, and they generate small amounts of electricity using anything organic that you can put in them. They take a couple weeks to set up depending on the experiments, but once they're up, they can just keep generating electricity as long as there is food for them. They have two 250 milliliter chambers, which is pretty good. Other kits that are sold are not nearly as big, and they're way more expensive. An easy experiment that doesn't require any lead time to get the experiment going is yeast and methyl blue. Just put it in one side with ferrocyanide in the other. Ferrocyanide sounds bad, but it's non-toxic. It's just kind of, it's a mediator, I guess. I don't know the science behind it, but put it in one side, it makes the electrons work. So it's easy, no setup time. Students can do it in a class period, and they can get demonstrable data out of it immediately, which we really like. We've also been working on lesson plans with teachers to meet New York State science curriculum requirements using the kits. Various lesson plan subjects that we have include, next slide, principles of MFCs, which include lab safety, common lab procedures, weighing, measuring, stuff like that. And then basic experiments, like the methyl blue experiment that I mentioned. Various substrates, something along the lines of every kid brings in a small sample of soil from their house or from a stream bed or wherever they want, and then they each plug it into a fuel cell, and they hypothesize which ones will be most effective in what situations, stuff like that. It's a great way to make them ask questions and learn about the scientific method. pH of substrate versus efficiency can teach the relationship between biology and chemistry, which is pretty cool. It's kind of hard to envision that sometimes. Series and parallel circuits is great for physics classrooms where they have to learn about Ohm's law, Kirchhoff's law, all that kind of thing. And then time-based circuits and circuit design is more for technology classes where they can really get into what components do, what capacitors are, how they can be used to do things with electronics, and that can be the power source for it. We're also working on educational videos, and we've noticed that too many videos are just boring lectures like this, like me talking. But on the other side of it, there's videos like Mythbusters, which are pretty much pure entertainment. They're played off as a science show, but there's not that much science to it. It's, oh, it didn't work the first time, let's blow it up. And I love the Mythbusters. Well, yeah, we want to do that too, but we want to have the science there too. And I love the Mythbusters. I've met Grant, actually. He was at he spoke at my school, but next slide. This is the happy medium we're shooting for. Bill Nye, we both grew up with him. He was always on TV. Anytime I turned on the TV, I wanted to see him. And he taught incredible scientific concepts without talking down to the kids while still being fun. And that's exactly what we're aiming for. We want it to be entertainment for people that want to learn. like I said, our target age group is ages 10 to 18, which we chose because it's at the age where they're starting to be able to get more sophisticated humor. We don't have to do like SpongeBob jokes and that kind of thing. But they're also able to have a basic understanding of scientific principles and lab techniques. So again, we don't have to talk down to them. And also, they're starting to think about their future. We want to kind of change the trajectory of kids' lives and be able to say, hey, STEM is an accessible thing. This is something that's fun. This is what you should want to do. And getting people at that age, we think, is a great way to do it. And we want to work with teachers and students to develop the content for them to get both high-quality information being thrown out there, but still keep them entertaining. And that's part of the iterative design process. Develop an idea, go back, get some feedback, go back to the beginning, try it again, tweak a couple things, get some more feedback. And eventually, we get the perfect happy medium of entertainment, information. That's what we really want to do. We also have some contacts in the fields, and we'd be able to bring them in for interviews in the videos to keep everything current and modern, and just expose some really cool stories about the fuel cell industry. And we do want to grow, like I said. We have a commitment to growth. And the easiest way for us to do that is to have teachers that can bring us into their classrooms, have us lecture, have us speak, have us work with their kids. Next slide. And we also want some students to help us out. That's the easiest way for us to learn about how students learn, is to just meet with students, talk to them, work with them. So that's where we want to go from here. And thank you very much.
If I could say, a couple more things on that. Brian mentioned it, but we really can't underscore enough. One of the huge values of this technology is all the concepts covered really are very scalable. It's very intuitive for kids as young as 3rd grade to be able to say, all right, I don't really know what's going on, but you're telling me the microorganisms are making energy, and they live on that stuff, so if there's more of that stuff, there's going to be more microorganisms and more energy. And if I feed them more, then they're going to make more energy. And so you can plant those seeds early, and then as they start to grow, they have this real hook to, if you're powering an LED, say, well, that's great, but I want to power something more. Let's make these suckers do something. And then they go, well, okay, so if it's, what do I feed them? I gave them more of this stuff, maybe I can tweak that a little bit. How does that work? And before you know it, and we've seen it happen, which is the really cool thing, is when we did this tech ed class, I'd come in about 2 to 3 times a week, and whenever I came in, kids were bringing me their own questions. We started for the first couple of times, I'd give the pitch kind of a thing and say, hey, here's what's going on, and boy, isn't this neat. And, they are at school as excited as they are, so they're kind of rolling their eyes a little bit, particularly on a Friday. We're at a last period. But then before I know it, I'm coming in, and they go, oh, hey, good, you're here. And then you pull over the notebook, and like, what about this? What's this all about? So that's really important. You get that hook in, and it allows kids as well to explore what they're interested in. Because again, you can go online, and someone might say, wastewater treatment, yeah, I guess that's a big problem. I don't really, not so much worried about, the electricity production, but, I really like the idea of, wastewater treatment. We ought to take care of that. And before the kid knows that he's doing it, he's laying the foundation for a environmental engineering degree. So it allows kids to get a sample of all this stuff before they get there. The other thing is particularly well suited for biology. I had a very good science program at my school, but biology in particular suffers from, it's very difficult to do quantitative experiments in a high school setting. Some of the most simple ones, even just looking at cell growth, require a piece of equipment known as a spectrophotometer, which basically just measures how blurry a sample is, how turbid it is. But that'll cost you a few $1,000s, and that's a used one. And then when the lamp blows, that's another at least 1,000. So, generally speaking, most high schools don't have the resources to do that. In contrast, you hook a multimeter up to this guy, and you can take data points of how your voltage is going up over time, and you can wind up with a cellular growth curve.
We're working to develop data loggers that do it automatically, constantly, that basically just beam the information to the cloud and you can access it from any computer as long as it's on a wireless network, which most schools have at this point. You can just set the experiments up, plug the, they're called electric imps, plug them into it, and then it'll just record the data every 10 seconds or hour or whatever, however frequent you want it to. And then you can just see the whole thing, export it as an Excel file, be able to chart it, add trend lines.
You know, yeah, that was one of the things, is when I did go to a research lab in college eventually, you know, that was the first time that I had ever tried to fit, you know, a graph to the data for the purposes of saying, you know, and therefore I can use this. That was the first time that I really understood the importance of the R-squared value in, you know, fitting a curve. So these kids, you know, whether or not they really dig into, you know, the mathematical theorem of how, you know, you wind up with an R-squared value, they're really able to interpret, oh, okay, it's a better fit, therefore I can say this, therefore, you know, you really take it all the way home, therefore my LED is going to blink more quickly. And that's really where you kind of put all of that together, and that's an amazing thing to view on a kid that young. And they can do it of their own volition and do it very intuitively. And you can go, you know, even further. Again, you know, we talked about competitive pressures we were talking about before. And one of the things that's, you know, powerful even at a college setting is the fact that, you know, unlike a traditional power supply, the load you place on them, you know, the traditional power supply, you know, whatever the load is, the chemistry doesn't really change much. But you push on the microorganisms and they push back because they have all of that complex biology that they can use to change what they're doing. So if you make it harder for them to breathe, they might start expressing different genes, start dwindling down different other pathways that aren't needed at that point in time. So you really push this whole interdisciplinary concept. And that's something that, frankly, you know, even in a professional research capacity, I still have issues doing with PhDs. The industrial field's very segmented. You have folks that are working on, you know, catalysts, for instance, that say, you know, well, I can do this. I'm really good at inorganic chemistry. We'll take care of this. I have no idea what's going on over there at the anode. You're a microbiologist. Those are bugs, right? That's your thing. You think you can take care of that for me? You can't do it that way. You know, it's all tied. It all has to be developed in tangent. And that's going to start to happen in more and more fields. So getting kids to, even if they don't explore it in depth, know how to approach an interdisciplinary situation, know how to talk to somebody who might be exploring something else and ask them the right questions and really develop that communication. That's amazingly powerful. That's kind of, you know, the other non-altruistic reason why we do this is that, you know, I'm going to need more employees, and I would prefer that they know how to do this stuff. But yeah, with that, you know, I guess we're going to be doing replacement. What time do we have? 10:45, so we got about half an hour. What I'd like to do, especially because there's only, you know, 4 of you here, that's great. We can do more Q&A. Obviously, we got plenty of time.
Do you want me to run down and get some?
Yeah.
Yeah, the kits that we have right now are, they've been running for a while, but the microbes get hungry, so we'll feed them with you using just cream and sugar from downstairs.
Right now they're going for ADPs, but you know what I'd really like to talk to you about is, you know, the program that we did at the high school. You know, they built it on their own. We do the kits because we know that not every classroom and not every curriculum would be able to do that. But the kids really got, you know, an enormous value out of taking that long amount of time and exploring a bunch of different things. I mean, this little, you know, box here, it didn't start as a box. You know, there's a couple other designs there. And, you know, the kids learn the difference between drawing something on paper, saying, oh, well, that should seal, and actually making it seal.
Does it have to be like airtight? And then
No, but at least liquid tight.
liquid tight, gotcha.
You know, and that's the whole thing is that, you know, that's why it wound up with, you know, a somewhat more simple shape. But again, you know, they milled out all of these parts and everything, so, you know, you're learning physical tooling processes, which is something that I didn't touch until, you know, I was in college, and I nearly took my hands off a couple of times. But, you know, again, they went through this, you know, this whole design process, and, you know, everything from, well, oh, that's why you actually have a gasket there. You understand that in a lot more depth when it's keeping sewage from spilling on your hands. You're a lot more motivated. But yeah, and you can see, you know, they used a carbon felt in this instance.
Did they just buy the carbon felt? Or did you use something?
I think they bought it. Most of these materials are pretty easily available. The felt can be kind of hard to come by in small quantities. That's another thing. What we're working on right now is because we are buying this stuff industrially, we should be able to offer small quantities on a much more cost-competitive basis. Again, we're not looking to gouge anybody on materials that cost 13 cents a foot. But independent of that, there are other alternatives. I would highly recommend Googling microbial fuel cells, how-to, or something like that. People will make these things out of pencil leads. That's graphite. There's ways to do that. You can use granulated activated carbon, which is available anywhere you can get aquarium supplies. That's kind of tricky because you need to compress it just a little bit so that you make sure it has good conductivity. But we use stainless steel wire as the current collectors in that instance. I describe it as like an electron highway. The carbon is conductive, but it is a little bit resistive, which means that the cells have to work that much harder to push the electrons. And if they're working that hard to do that, that's less energy that they have to light your LED. So we use the stainless steel, which is a lot more conductive, and kind of intersperse it so that the electrons have to travel the minimal distance through the carbon material. And again, look at the way that we're talking about that there. That's something that's fairly intuitive. You can talk about how hard it is for the material to go through there, and now, a kid will never understand conductivity better than when he looks at how fast the LED is going, in just something with carbon and then something after the current collectors. You can talk about, how that's arranged. The inner electrode spacing, as Brian mentioned, becomes very important because you can only get as much current flow as you have those hydrogen ions moving over. So, the processes are tied. You can really, the list just goes on and on and on, but there's so much you can do with it. And I should mention, if you build something like this, this is where you could use an aquarium pump and just have the air bubbling in. I think that's how we did this one. I know we did a air-breathing liquid cathode like that. Right now, we don't offer the catalyzed air-breathing cathode. The only ones that are really available for us to source are platinum-coated as the catalyst, and are therefore, that's not the price point we want to offer. We're working on developing a way to do the same ones that we do industrially, but because we're still tweaking that process, we can't really take somebody's money and offer them a product that we know is going to work, and that's, we'll be introducing that. It's not there yet. So what we use right now is a compound called ferrocyanide, and the way we usually explain it is as soluble oxygen. You get almost the same voltage because it has the same reduction potential, but unlike oxygen, it's readily soluble in water, which means that you can put it in there and you don't have to pump. It's fairly inexpensive. It's in most schools, I think. We've talked to a couple of them. Typical laboratory safety stuff is fine. It's not like it's particularly bad. But yeah, so that's what we got. If you guys want to come on up, if you have any more questions. Not so worried about the presentation. Yeah, so what did we say that we were at here? 63, great. So, glad you guys are around. So how we're going to do this here. So normally, what you'd do is you'd have kind of a, we can hope this guy's still watertight. See how this one goes. I would have you guys be doing this, but we did not think ahead and bring gloves. So if anybody gets sick, we'll put that one on me. These are also, yeah. Being a good Boy Scout. I do. There we go. Yeah, and good Boy Scout here. So yeah, normally I think we probably just over-tighten this because we wanted people to be able to handle them and not have it spill. But these are finger tight. You can get at them with gloves usually without tearing them, which is.
They're also standard, so you can put tubes in them.
Yeah. So. Yeah. The adapters for these, go for, a couple bucks, which adds up for a lot of, injection molded plastic. But you can get them pretty much anywhere. So you just drain it like that. We're only gonna do a little bit so that. Oh, no, it's fine, I think. I hope. It's not my table. They know where to find me. So we'll set that guy there.
And what did you say you loaded what was
So this is actually, well, originally, like a couple months ago, it was a sample from the Rensselaer County wastewater treatment plant.
What's in there now?
That is cream, milk, and sugar from breakfast yesterday. I think we're gonna take some of this. You know what? We'll do it this way. You're gonna have to get more water. So a really interesting thing is, you know, again, the power output changes depending on what you put in there. One of the easiest concepts to connect is that just the more energy you have in the food there, the happier the bugs are going to be. But it even goes a step further. You know, obviously the bugs are more than happy with the glucose and whatnot, but there's this really interesting thing that happens with, remember before we were talking about those hydrogen ions migrating through. They tend to do that better with more complex substrates, because you have a lot of organic bases that will act almost as shuttles to move that stuff around. So the hydrogen ions will have someone to hitch a ride with over at the cathode that's present at a higher concentration. On an industrial standpoint, this actually means that we do okay with wastewater, but we do a lot better with, you know, effluent that's coming from a cheese factory, for instance. So we'll go right ahead, shake this guy up.
How about like just you have to literally leaves
Mm-hmm.
and kind of biodegradable stuff. You just chop it up and put it in water?
Absolutely. And then right now, you know, a lot of that's really more on a cost-effective basis. That's more on the physical end. We haven't run a lot of those experiments with the kits. I'm looking forward to it. I'd like to get to that point. And as I said, we're looking for people to play with our stuff and let us know how it went. But I'll just poke a quick hole in here so that we don't have that nice tight seal. No, yeah, that's not going to work. All right. Oh,
Why don't you take the thing out of here and then just pour it in there?
I like you. So yeah, clearly, I mean, one of the things we have in our instruction manuals is how well these syringes can act as a funnel. And
You don't even need to
yeah, well, let's.
use the syringy part.
No. Yeah. And you want to do your best to get most of the air out. Ooh. We're going to go ahead and move the iPad here. Why don't you take that? You want to do your best to get most of the air out, but if there's a little bit, it's really not a problem. And the other thing you can actually do is, with those lure lock fittings, is run some tubing and hook it up to a balloon. Depending on what you have going on, the gaseous products of the respiration will actually start to fill it. Otherwise, you actually do wind up with just a little bit of pressure, which is actually kind of funny when the kids go to open it. You know, but yeah, so.
So if it's anaerobic, does it actually, it doesn't ferment, does it?
Parts of it will. So the microbes are actually pseudo-anaerobic. They're not using oxygen, but there's oxygen on the other end, so the biology is practically as if it was aerobic respiration. But because you have other organisms in there, you will wind up with anaerobic processes happening. And that's, you know, again, if you really wanted and you had the students, you could develop an experiment to validate that, because it changes the more pure your culture is, the longer you have it running. There's just all sorts of stuff. It's a lot of fun. And actually, you can use compounds that inhibit only anaerobic microorganisms, the ones that generate methane. Those, I think, are a little more toxic. We don't use them. I don't know if you could use them in a classroom setting, but there are probably analogs to that. But enough talk. Let's see how this guy did. This is going to be really embarrassing if he didn't do particularly well. His cells are a little old, though, so that is a possibility.
So tell me again, if, as you're doing that, do two things.
Oh, that
if
went
I-
down.
if I
That's
got the
bad.
kit,
Mhm.
how do I get the microbes? Because they're kind of special microbes. Or
Yes, you can. You'd have to isolate them. So
you
we're.
don't supply the microbes?
Depends on how local you are. I don't know the legality of us moving those around through the USPS right now. So, you know, I'm on enough watch lists as it is. But if you're local, we can absolutely drive them out to you, no problem, that kind of thing. So this actually went down. Now, there's a couple of reasons for that. I think if we leave it, part of it is that when you introduce that oxygen there, now the bugs wind up dumping oxygen onto that as opposed to the electrode. It's the same thing. It's almost as if we're getting a lot of crossover there, like in that other fuel cell. The membranes help, but they don't solve all of it. But I think if we've got some of this left over, I'm going to go ahead and add it to this guy. And also, we'll have these down in the trade show area later. This guy's at 165. At the trade show area later, and I'm willing to bet. Yes, yeah. And I'm willing to bet that at this point, this guy will be more back up to speed, because most of the oxygen that is in there, diminishing that, would have been consumed. Make just a little bit of room on this guy. Ooh, wow, that looks tasty. Yep. Yeah, and this is obviously a little lacking in scientific rigor, but that's okay. What it lacks in rigor, it makes up in nastiness, I suppose. Ooh, yeah, that one's cranking. You can smell the biological activity on that one. Sorry about that. Like I said, I have a uniquely understanding roommate. It depends on which definitions of employment we're looking at. It's been really difficult to provide meaningful employment for a lot of the folks. But we have, it's me and Brian, obviously, doing the educational stuff. And then we have a number of interns that work for us on kind of a part-time basis. So I'd say we're probably about 6 strong, give or take, which isn't a lot, but it turns out it's been enough. We're in some interesting conversations with some industrial folks, some of them international, just because we were able to get the data that we needed. Yeah, so it's been a very interesting story. Yeah, I think, let's see.
So in a classroom, how often would you refuel?
Probably about every 2 weeks. And a lot of that, and that's why I'm kind of surprised that the voltage is dropping off on these already. But a lot of that, you actually start to see, right? So that's one of the things is that, because of the time intensive nature of this, it doesn't fit into a real classroom setting to do some of the longer term experiments. But what you can do is set up a class just to set up the reactors. And from there on in, even on the order of months, can be, okay, class is starting, write down the homework, check the voltage on your reactor and record it in your notebook. And what you'll start to see is very clearly you see the voltage rise and then drop. And then you refuel it, rise higher, and then drop. And then you refuel it and rise higher. I'm going to stop waving this in front of your face. But, yeah, speaking of safety. Yeah. But, yeah, so I think that kind of answers your question. But if you can keep plants in your office, you'll be just fine with these. Okay, so this guy's back at 165, and we didn't add as much to that. Well, this is a failure of a demonstration, I think, but I promise you, it's not garbage. This generally, does work.
What would you expect?
I would have expected this to be closer to about 1/2 volt. And the other thing, in terms of the power output, that's also dependent on, again, the resistive load. And that's another great lesson to teach kids, is that it's tied. It really drives home the difference between voltage and power. Kids really learn, you can set up a circuit that blinks with the total amount of energy. So you set up the circuit such that when the capacitor has X amount of joules, it blinks. And that's independent of the voltage that's coming off of this. So what you can do, though, is at a very low resistance, the bugs are breathing a lot. There's a lot of electrons moving, but they're moving at a very low pressure, a very low voltage, so there's less energy per electron. At a really high resistance, the bugs have to work harder to get those electrons out, so those electrons are moving at a much higher energy, but there's fewer of them going. And what that means is that if you were to graph power versus voltage, you wind up with a curve. The peak being somewhere in the middle, and that determines the optimal resistive load on there. But it's really special because it helps to drive home the difference that a higher voltage does not necessarily mean more power out of a system. And also, if you look at the equation for that, it's power equals V squared over R. Now, at some point in high school, kids start doing parabolas. Your A squared plus B squared equals C squared. No, that's the other P guy. But the point is that you see the squared term, and that's just one more point to say, oh, hey, you remember that stuff in math class and that stuff that we covered in the kinematics earlier in the year? Well, here it is again. And
Is that the formula to
oh, yeah, absolutely. Yeah, the V squared over R, the fact that you have the squared term for the variable is why you get that curved shape. And you really don't have to explore it in a lot of depth there, but it's nice to be able to point that out to kids and say, yeah, by the way, you'll start to see more and more of this because we teach you that math for a reason. So let's see how this guy's doing here.
And it'll also be more effective if you use laboratory-grade sucrose that is better than just half and half.
Yeah.
Although it does work.
What were we at when we started here? Yeah, we're about halfway back up there now.
You had mentioned specialized microorganisms that you use that you can't ship. Can you use something like what they use for your septic tank?
Oh, yeah, absolutely.
Is that the same kind of microorganisms that we're talking about?
Not all of them, but it'll lead to their growth. That's actually one of the things.
Because that's readily available at the dollar store. You can buy that. Yeah, Ridex.
Yeah.
Break down solids in your cesspool.
Let me see. I know they used it, but I would love if I could pull out that note here. Oh, yeah, here's some of the CAD that they did originally. Yeah, so they tried doing that bottle reactor. But you quickly learn how hard it is to get PVC to seal on a wall that's this thin. Yeah, so, and that's, like I said, though, that's great because I work with, some, academic biochemists, and they'll ask me to build stuff for them. They're like, oh, yeah, it's pretty easy. You just got to do that, right? I'm like, and I was one of those. My background's biochemistry, so I was that guy for a while, too. But, yeah, let's see. Yeah, here's a lot of notes on the actual construction, which is great. I think that's actually.
Use the metal water bottles.
So,
that are
yeah.
out now, and maybe even be able to do a simple MIG welding to
Oh, wow, yeah.
between the tubes to get it to seal up.
Yeah.
I don't know how thick the walls are on the
They're very
water
thin,
bottles, but
and I don't know how good the alloy is for welding.
Yeah.
I'm sure it's made for die forming instead of being able to be welding, but I'm sure it's possible. I just don't know how clean it would be, whether it would just burn through.
And another thing.
that itself, just kids trying to experiment with different.
Yeah,
Exactly.
That's exactly what we like. Just
And
what if this? What if this?
yeah, and
That's the most exciting part.
you have to be a little careful about what metals you use, because some of them that are more apt to corrode will actually give you a falsely positive voltage. But that's another great thing to take a look at, though, is that if you got a kid there, biologically, the most you're really ever going to see out of these is about 0.7, 0.8 volts, unless you take a bunch of them and wire them in series, which is another great lesson. But that's a great thing there, is you can say, well, geez, yours is getting 2.5 volts. I don't know what's going on with that. I made mine out of a different metal. That's a great connection for them. But generally speaking, anything 316 or higher as far as stainless steel goes, that's fine. If you're doing like high-level academic research, the papers, you'll have other people nitpicking at you, but it's totally fine. Yeah, and I think this has some of our contact stuff. Clearly, like I said, we're in our early stages here, so we would have hoped to have had more of a demo for you guys. But if you have any questions, or you ever want to bounce something around or get involved, we're more than happy to do that. We've mentored a couple of students independently. We've worked with a couple of schools. Happy to do it. I'd love to do it. This is the stuff that keeps me sane.